Hello friends, this is our crash program or revision program of physics for NEET and JEE, and this is our sixth topic, rotational motion. This topic we are starting with the point the center of mass. Center of mass is a point where whole mass of a body is assumed to be concentrated. For symmetrically shaped bodies, center of mass lies at its geometric center. As an example, we can say for a sphere, its center is assumed as the point where whole mass of the sphere is concentrated, that is the center of mass. You can see in the table that for a cone or pyramid, center of mass lies on the axis of pyramid, at a distance 3h by 4, from the vertex, or we can say at a distance h by 4 from the base. Particle means a point mass whose dimensions are negligible, and every rigid body, whatever may be its shape, it is assumed as combination of numerous point masses. For a system of particles which possess masses m1, m2, m3, etc., and their position vectors are r1, r2, r3, etc., then position vector of center of mass can be calculated using the equation m1r1 plus m2r2 plus etc. plus mnrn all divided by m1 plus m2 plus etc. plus mn. Or you can give total mass of the body at the numerator. M1 R1, what is R1? R1 is the position vector of a particle M1, and what is R2? Position vector of a second particle M2, like that. So this is the equation for position vector, and that position vector we can split into three components, x, y, z. So x position of center of mass, xcm, we can say m1 x1 plus m2 x2 plus etc. plus mn xn all divided by total mass m1 plus m2 plus etc. plus mn. Okay, like that we can calculate y position and z position, m1 z1 plus m2 z2 plus etc. plus mn zn all divided by m1 plus m2 plus m3 etc. mn. Total mass comes on the denominator. This is the equation for position vector. Then what will be the equation of velocity of center of mass? It can be calculated using d by dt of RCM, because velocity is rate of change of position. So we can apply here d by dt of RCM. So we will get m1 v1 plus m2 v2 plus etc. plus mn vn divided by m1 plus m2 plus etc. plus mn. Like that we can say acceleration of center of mass ACM equal to d by dt of velocity of center of mass, or we can say d square by dt square of position vector of center of mass. That we can say M1A1 plus M2A2 plus etc. plus Mn divided by M1 plus M2 plus M3 etc. Okay, you can see the question here. The distance between the carbon atom and the oxygen atom in a carbon monoxide molecule is 1.1 angstrom. Given mass of carbon atom is 12 AMU and mass of oxygen atom is 16 AMU. Calculate the position of center of mass of the carbon monoxide molecule. In carbon monoxide molecule, carbon, oxygen, two atoms are there. So here we need to take only one axis. Here we need to take only one axis. I am giving x axis. For two particle system, only single axis is needed to find its center of mass. We can take x position of center of mass. So the position of carbon is taken as O, origin. Okay. Why I took position of carbon? In the question you can see this position of center of mass we have to calculate from carbon. So we are taking carbon at origin. Okay. Then what is x value of carbon? 0. X value of carbon is 0. And what is the x value of oxygen? But here we can say x1 equal to 0. And what is x value of oxygen? Distance between carbon and oxygen is given as 1.1 angstrom. Then we can say x value of oxygen, x2 equal to what? 1.1 angstrom. x2 equal to 1.1 angstrom. Now you can find position of center of mass using this equation. Here we have only one axis, x axis, so we have to find only the x position of center of mass. So m1 x1 plus m2 x2 divided by m1 plus m2. m1 mass of carbon atom is 12 AMU. Okay, AMU will come on numerator and denominator, then it will be cancelled out. No need of changing the unit of AMU into SI unit, kilogram. Okay, because when ratios are coming, units will be cancelled. So 12 AMU into x position of carbon is 0 plus 16 AMU for oxygen into x position of oxygen is 1.1 angstrom divided by m1 plus m2. 12 plus 16, that is 28 AMU. AMU will be cancelled out and we will get x position of center of mass in angstrom. 16 by 28. We can solve it with 4 by 7 into 1.1 angstrom. Then we will get 4.4 angstrom by 7. And from the options, what are the options given? 6.3 angstrom from the carbon atom. Option A is wrong. Option B is also wrong. It will not be 1 angstrom. 0.63 angstrom from the carbon atom. Okay, 0.63 angstrom from the carbon atom. So total distance is 1.1 angstrom. So we will get position of center of mass away from carbon atom 0.63 angstrom and near to oxygen. That means position of center of mass is inversely proportional to mass of the particle. That means as mass of the particle increases, distance of center of mass from the mass decreases. So here mass of oxygen is greater, so center of mass lies near to oxygen and center of mass lies away from carbon. And for identical masses, center of mass lies at the middle. And here I am giving you an example, an important question that asked many times in various entrance exam. For a solid sphere, center of mass lies at the geometric center, whose radius is capital R. If a solid sphere of radius r by 2, a solid sphere of radius r by 2 is cut from the solid sphere, then what happens to its center of mass? Initially, this was the center of mass of the whole sphere, its geometric center. If a sphere of radius r by 2 is cut out of the solid sphere, then what happens to its center of mass? Its center of mass shifts to r by 6 from the old center of mass. To the left if the sphere is cut from the right, or to the right if the sphere is cut from the left, like that. Next, we are discussing moment of inertia. Moment of inertia is actually does the role of mass in rotational motion. So we can say moment of inertia is rotational analog of mass. Rotational analog of mass. To find moment of inertia, the body should be rotating. This is the axis of rotation, and here we have a mass m, and the mass m rotates about this axis of rotation. Then we can take r is the perpendicular distance of the mass from the axis of rotation. So moment of inertia I equal to, we can say, mr square. Moment of inertia I equal to mr square for a point mass, for a single point mass. Okay, from here we can find its unit and dimensions. Kilogram meter square is the unit of moment of inertia. Now if a body is rotating about axis of about 10 axis, then we can say each particle on the body m1 possesses r1 distance from the axis of rotation, and if I am taking m2 here, m2 possesses r2 distance from the axis of rotation. Like that, different point masses of the body possess different distances from the axis of rotation. In that cases we will say moment of inertia equal to total mass into k square. Capital M denotes total mass of the body and k denotes radius of gyration. Radius of gyration, or you can pronounce radius of gyration. From here we can say total moment of inertia of the body I equal to I1 plus I2 plus I3 plus etc. plus In. Okay, how many point masses are there? Their moment of inertia we have to get, we have to add it up to get total moment of inertia of the body. That means I equal to m1 r1 square plus m2 r2 square plus etc. plus mn rn square. And here you can see we are taking all mass particles are identical. That means m1 equal to m2 equal to m3 equal to etc. They are same as m. So I equal to, we can take to small m. Small m means mass of point mass outside r1 square plus r2 square plus etc. plus rn square. Okay, and for I can give total mass into k square. Total mass into k square, or k is radius of gyration, and I am multiplying with n here. N is the number of mass particles, nm. So I have to divide the term with n. Rn square divided by n. And I am multiplying with the n here, I have to divide the term with n. So we can say mk square equal to n into m means total mass of the system or body, that is capital M, into R1 square plus R2 square plus etc. plus Rn square divided by N. M cancels, right? Then what is K? Radius of gyration K equal to square root of R1 square plus R2 square plus etc. plus Rn square upon N. This is the radius of gyration of system of particles. Radius of gyration is the root mean square of distances of mass particles from the axis of rotation. We can say RMS distance of root mean square distance of particles from the axis of rotation. From the axis of rotation. This actually indicates, this K actually indicates the distance of perpendicular distance of the point where whole mass of the body is concentrated from the axis of rotation. There are two theorems to find moments of inertia of rotations of bodies about various or different axes. First theorem is parallel axis theorem. Using parallel axis theorem, we are finding moment of inertia of the body when it is rotating about an axis parallel to the axis through the center of mass. So, ICM is the moment of inertia of the body when it is rotating about an axis through the center of mass. About an axis through the center of mass. And capital M is the total mass of the body and A is the distance between the two axes. Distance between the two axes means ICM and new axis of rotation. Okay, that is called parallel axis theorem. Perpendicular axis theorem. Okay. We have moments of inertia of two axes in the plane of the body. Then moment of inertia about an axis perpendicular to the plane of the body is found using Iz equal to Ix plus Iy. Iz equal to Ix plus Iy. Once more. We know moments of inertia of the body about two perpendicular axes in the plane. Then moment of inertia of the body about an axis perpendicular to the plane, that is Iz is found using Ix plus Iy. Listen. For a ring which is rotating about an axis perpendicular to its plane, which is rotating about an axis perpendicular to the plane, moment of inertia I equal to m into r square. Moment of inertia I equal to m into r square. The whole mass of ring lies at its circumference. Whole mass of the ring lies at its circumference. So distance of all mass particles from the axis of rotation is same, that is equal to radius of the ring. Okay, that moment of inertia I equal to total mass into radius square. Okay, then what is the moment of inertia if the ring is rotating about a axis parallel to this I? So this I we can take it as ICM, moment of inertia of the body about when it is rotating about an axis through center of mass, because for the ring center of mass lies at the midpoint geometric center. ICM is mr square. Then to find moment of inertia about an axis, tangential axis parallel to ICM is found using our theory what parallel axis theorem. That is found using I equal to what? ICM plus MA square. ICM is MR square and M into what is A? A is the distance between the axes, that is also radius square, radius here. So we will get I equal to 2 mr square. I equal to 2 mr square. Okay. Then what will be the moment of inertia about an axis in the plane through center of mass? What will be the moment of inertia about an axis in the plane of the ring? Okay, how can we find it? To find moment of inertia about an axis in the plane ID, okay, diametrical axis, moment of inertia about diametrical axis ID, and just taking one more axis in the plane, okay, which is perpendicular to what? The earlier axis. So we can take this as IX and this as IY. So we just studied IZ equal to what? IX plus IY. And for a ring, IX and IY are identical. Both are same for a ring. Okay. So IX equal to IY equal to, we can say, ID. So IZ equal to 2ID or ID equal to what? IZ by 2. What was IZ here? IZ means axis perpendicular to the plane, that we already wrote here. It is mr square. So ID equal to, we will get mr square by 2. Okay, using perpendicular axis we found moment of inertia about diameter of the ring. Okay, now you can see a table. There. In that table, you can see axis of rotation, body, and moment of inertia. K means radius of gyration, and k square by r square. Okay, k square by r square we use in case of rotational kinetic energy. Okay, that we will discuss. For a ring, moment of inertia, as we discussed, its moment of inertia I equal to what? Mr square about an axis perpendicular to the plane through center of mass. So I equal to mr square, and the general relation of moment of inertia is mk square, where k is the radius of gyration. So by comparing we will get k equal to what? R. Okay, by comparing moment of inertia equation with the mk square, we will get moment of radius of gyration that we are seeing in that table. Okay, and then k square by r square is equal to 1. Now you are seeing in the board is moment of inertia of disk about various axes, and the first you can say about an axis passing through the center of gravity and perpendicular to the plane. That moment of inertia is mr square by 2 or half mr square. That moment of inertia, when we are comparing with the main equation of moment of inertia mk square, then we will get k square equal to r square by 2, or k square by r square we will get k square by r square we will get 1 by 2, k square by r square equal to 1 by 2, and k equal to, we will get r by root 2, where k is the radius of gyration of the disk about an axis passing through the center of gravity and perpendicular to the plane. And using perpendicular axis theorem, we can find moment of inertia about an axis through diameter, that is given there mr square by 4. Solid cylinder. For solid cylinder, its moment of inertia is mr square by 2, same as that of disk. And you can see about an axis, about a tangential axis. Moment of inertia is given by 3 by 2 mr square. That is found using parallel axis theorem. What was that theorem? I equal to ICM plus MA square. So I equal to, what is ICM? ICM through center of mass, it is mr square by 2 into m, radius is r square. Then we will get 3 by 2 mr square. Okay, the tangential axis of cylinders is called generator axis. And for cylindrical shell, you can see moment of inertia mr square like ring. Cylindrical shell or hollow cylinder is just like thin ring, because the entire mass is concentrated, or entire mass is distributed on the circumference only for the ring and for the hollow cylinder. Okay, that's why their moment of inertia mr square. And next you can see solid sphere, very important one, which is also mentioned in NCERT textbook, that we can use in case of earth. Its moment of inertia about any axis through its diameter is 2 by 5 mr square, and k, radius of gyration of the solid cylinder, is root of 2 by 5 into r. Okay, that k square by r square also you have to try to by heart 2 by 5. Okay, and about tangential axis we can find using parallel axis theorem. 2 by 5 mr square plus ma square, or that a equal to r, then calculating we will get 7 by 5 mr square. And you can see long thin rod. For long thin rod, moment of inertia about an axis passing through its center and perpendicular to the rod is ml square by 12, and about an axis passing through its edge and perpendicular to the rod is ml square by 3. It is also found using parallel axis theorem, ICM plus ma square. This is ICM, and this is the axis through edge. Moment of inertia about an axis through the edge. So I edge equal to what? ml square by 12 plus what we have to do? ma square. What is a? A is actually half of length of the rod. So we will get ml by 2 whole square. ml by 2 whole square. By calculating we will get ml square by 3. It is the moment of inertia about an axis perpendicular to the plane and passing through its edge. These are the equations given in NCERT textbook. Some special bodies. Spherical shell, about its diametric axis, moment of inertia is 2 by 3 mr square. Annular disc with inner radius r1 and outer radius r2, half into m by 2 into r1 square plus r2 square, that you can by heart. And you can see solid moment of inertia of solid cylinder about an axis passing through its center of gravity and perpendicular to its own axis. In the earlier case, we discussed the moment of inertia about the axis of cylinder. For hollow cylinder, it is mr square, and for solid cylinder, it is mr square by 2. Here, the axis is given perpendicular to the axis of cylinder. It is found using m into l square by 12 plus r square by 4 with inner radius r1 and outer radius r2, same as the case of annular disc, and hollow sphere with inner radius r1 and outer radius r2. Okay, and here one more case, you can see rectangular lamina of length L and breadth B, moment of inertia about a perpendicular axis passing through the center of mass is given m by 12 into L square plus b square. You just add moment of inertia about length and breadth. About length you will take ml square by 12 and about breadth you will take mb square by 12 and you will just add them m by 12 into L square plus b square. It is the trick to by heart moment of inertia of rectangular lamina. And for ellipse with semi major axis A and semi minor axis B, moment of inertia about an axis passing through the center perpendicular to the plane is m by 4 into a square plus b square. And for solid cone 3 by 10 mr square, and for equilateral triangular lamina it is ma square by 6, where a is the side of the triangular lamina. Okay, try to by heart moment of inertia of special bodies also, then we can solve the problems quickly and very easily. Here is the question. Moment of inertia of a uniform circular disc about a diameter is I. Its moment of inertia about an axis perpendicular to its plane and passing through a point on its rim will be. Options are the 5i, 6i, 3i, 4i. You just pause the video and try to solve it. A disc, axis along diameter, moment of inertia I. This moment of inertia we already studied in the table, that mr square by 4 for disc about diameter, mr square by 4. Then what was the question? What is the question? Moment of inertia about an axis through the rim perpendicular to the plane. Through the rim perpendicular to the plane. So, this is the condition. This is the condition. This moment of inertia for this axis we already studied the moment of inertia for disc ICM perpendicular to the plane, mr square by 2. So, I dash equal to what? ICM plus ma square according to parallel axis theorem. What is ICM? mr square by 2 plus m into r square. Then we will get 3 by 2 mr square. We will get 3 by 2 mr square. Here id equal to mr square by 4. This is given as I in the question. So I am multiplying with the 2 on numerator and denominator. So we will get 3 into 2 by 4 mr square. 3 into 2 is 6. 6 into mr square by 4. 6i is the answer. Next question. 4 thin rods of same mass m and length L form a square as shown in the figure. Okay. Moment of inertia of this system about an axis through center O and perpendicular to its plane is. Options are the 4 by 3 ml square, ml square by 3, ml square by 6, 2 by 3 ml square. You just pause the video and try to solve it. Moment of inertia about the perpendicular plane through the center of mass of a long rod, thin rod is I equal to, we studied that ml square by 12. Here length is given as smaller, ml square by 12. So, due to a single rod, moment of inertia at O perpendicular to the plane, what will be the distance? We can apply per parallel axis theorem. I equal to ICM plus MA square. This is ICM. The point O lies parallel to the axis perpendicular to the plane at O is actually parallel to the axis perpendicular to the plane through center of mass. So, ml square by 12 plus m into total length of rod is L, so half of length is L by 2, so L by 2 whole square. Solving we will get what? ml square by 3. This is moment of inertia due to a single rod. 4 rods are there. So net moment of inertia I net equal to 4 into ml square by 3. Okay, next question. 3 rings, each of mass capital M and radius R, are arranged as shown in the figure. Moment of inertia of the system about y dash will be. Options are the 3 mr square, 3 by 2 mr square, 5 mr square, 7 by 2 mr square. Just to try to find it. For first ring, the axis passes through its diameter, right? So moment of inertia is mr square by 2. And for second and third ring, the axis passes through the rim tangentially, okay, parallel to the diameter. Once more, for second ring and third ring, the axis passes through the rim parallel to the diameter, so I2 and I3 we can calculate using parallel axis theorem. What is that equation? ICM plus MA square. What is ICM? That is I1 mr square by 2 plus through the center of mass along diameter, parallel axis along diameter. For ring, moment of inertia is mr square by 2, that we already discussed, mr square by 2 plus ma square, that distance is r, radius mr square, so we will get 3 by 2 mr square. So I2 and I3 both are 3 by 2 mr square. Then what is the total moment of inertia? I net equal to what? I1 plus I2 plus I3 mr square by 2 plus 3 by 2 mr square. Sorry, mr square by 2 plus 3 by 2 mr square plus 3 by 2 mr square. Half mr square plus 3 by 2 mr square plus 3 by 2 mr square. 3 by 2 mr square plus 3 by 2 mr square, we will get 3 mr square. 3 mr square plus half mr square, we will get 3.5 mr square, that is 7 by 2 mr square. What is torque? Torque is the rotating effect or turning effect of a force that is found using vector r cross f, where r is the perpendicular displacement of the point from the axis of rotation where the force is applied. What is r? R is the perpendicular displacement of the point of application of force from the axis of rotation, and the torque is found using tau equal r cross f, and torque is the rotational analog of force. What does force in translational motion? That is the duty of torque in rotational motion. So force F equal to ma, force F equal to ma, so comparing we will get torque tau equal to, instead of mass we will take moment of inertia, and instead of acceleration, angular acceleration. So torque tau equal to I alpha, and alpha is angular acceleration that we already discussed in the chapter motion in a plane. If net torque acting on a system is 0, net torque acting on a system is 0, then the body is in, or then the system is in rotational equilibrium. Here you can see a table. Okay. In the table you can see first case. A rod is there. Equal and opposite forces are acting on the rod at the same point. Forces are equal and act along the same line. Then forces will be cancelled out. Okay, sigma F or F net equal to 0 and the body will not rotate. Torque is also 0. That means body will remain stationary if it is initially at rest. Why such a statement? If it was initially at rest, it will remain at stationary. That means if the body was initially moving with a velocity, if net force is 0, the body will continue to move with the same velocity according to Newton's first law of motion. Every body continues in a state of rest or uniform motion unless compelled by an external unbalanced force. Now you can see the second case. Forces are equal, but they act at different lines. They do not act along the same line. Then what happens? Then also net force on the body is 0 because force acts equal and opposite. So net force is 0, but the rod will start to rotate. If this is the rod. In first case, equal and opposite forces are acting at the same position in opposite direction. Net force is 0 and net torque is 0. No rotation, no translation. In the second case, what we discussed, equal and opposite forces are acting at two different positions. Then what happens? Net force is 0, but the body will start to rotate. Body will start to rotate. Okay. Then we can say body is in translational equilibrium but not in rotational equilibrium because net torque cannot be 0. Body will start to rotate or spinning. Now you can see third point. Forces are unequal but act along the same line. Two forces are acting on the body at the same point in opposite direction, but one force is greater than the other. Then what happens? Body will move in the direction of bigger force. Translation will be there, but no rotation. Okay. Forces are unequal and act along the same line. Third point. Okay. Net force not equal to 0, but sigma tau, net torque is 0. Translation, body slipping or skidding. No rotation. And the last case. Unequal forces are acting on the body. Unequal forces are acting on the body. And they are acting at different positions. Then what happens? Net force cannot be 0. And body will rotate also. Then what happens? Body possesses rotation and translation. Body possesses rotation and translation. Body will tend to move. Body will tend to move in the direction of greater force and body also rotates. Then what happens? Position of the body will change and then also body will rotate. That type of motion is called rolling motion. That type of motion is called rolling motion. Combination of rotation and translation. Beam balance, or we can say seesaw. Okay. Here the balance is supported using a pivot, or it is suspended using a thread, whatever it may be. Okay. Then forces are acting at two ends, F1 at left end and F2 at the right end. Both forces are acting simultaneously in the same direction, then this pivot should give a reaction upwards. Okay, then each force will try to provide rotational motion. Okay, here we can say this is the length L1 part. Okay, and this portion is the L2 part. Then both the force tends to rotate the beam balance. If it is in rotational equilibrium, we can say torque due to F1 cancels torque due to F2, that is net torque equal to 0. So we can say at rotational equilibrium, net torque, tau net should be 0, that is tau 1 equal to negative of tau 2. Their directions are in opposite sense. Okay, tau 1 is R cross F, here L1 cross F and theta is 90 degree. L1 cross F, theta is 90 degree, no need of sin theta, sin 90 is 1. So L1F or F1 L1 equal to F2 L2 when we are taking the magnitudes. So we can say load into load arm equal to effort into effort arm. How? Load into load arm equal to effort into effort arm. This is the principle of beam balance. Okay, then only beam balance will be in rotational equilibrium. Load into load arm equal to effort into effort arm. Angular momentum is rotational analog of momentum. That means angular momentum does the role of momentum in the linear motion or translational motion, and it is found using vector L equal to vector R cross P, and we can write the magnitude as L equal to what? Rp sin theta. P is momentum mass into velocity, mvr sin theta. If the angle between velocity and radius vector is 90 degree, then angular momentum is simply mvr, mass into velocity. R is the perpendicular distance of the body from the axis of rotation. Okay, momentum P equal to mass into velocity. So we can say L equal to I omega. Moment of inertia does the role of mass in rotation, and omega does the role of velocity in rotation. Omega is the angular velocity. So L equal to I omega, like P equal to mass into velocity. And we studied that force F equal to rate of change of momentum, F equal to dP by dt, according to Newton's second law of motion. Like that, instead of force we can say torque tau equal to dP by dt dL by dt. Torque is the rate of change of angular momentum. So we can say if net torque acting on a system of particles is 0, if tau equal to 0, then we can say dL by dt equal to dL by dt equal to 0. If dL by dt is 0, if torque equal to 0, dL by dt equal to 0. Rate of change of angular momentum 0 means no change in angular momentum. L equal to constant. For L we can give equation I omega. So we can say I omega equal to constant, or we can say R cross P equal to constant. R cross P equal to constant, or we can say I1 omega 1 equal to I2 omega 2, or we can say R1 P1 equal to R1 cross P1 equal to R2 cross P2. Okay, this is law of conservation of angular momentum. If there is no net external torque is acting on a system of particles, its angular momentum remains conserved. Just like we discussed law of conservation of linear momentum. We can discuss lots of examples for successful application of conservation of angular momentum. Here I am discussing only one example. You can see a diagram on the board that a person carrying heavy weight in his hands and standing on a rotating platform can change the speed of platform. How? When the person suddenly folds his arms, moment of inertia decreases and in accordance with angular speed increases. When the person stretches his hands, moment of inertia increases, speed of rotating platform decreases, and when he folds his arm towards his body, then what happens? Moment of inertia decreases, so speed of the rotating platform increases. Effect of change in radius of Earth for its time period of rotation. We know that Earth is rotating about its own axis, and time period of that rotation is around 24 hours. Okay, L equal to I omega. L equal to I omega. For Earth is assumed as a sphere, a solid sphere, so its moment of inertia is 2 by 5 mr square, and omega we can write 2 pi by t. 2 pi by t. Then if angular momentum remains constant, if there is no net external torque, then we can say 2 by 5 m mass is constant, so we can say time period of rotation is directly proportional to square of time period of rotation is directly proportional to square of the radius of Earth. Okay, you may get confused with Kepler's law of periods, that t square proportional to r cube. That time period is actually time period of revolution of Earth around the sun. So don't get confused with it. Okay, that we will discuss in the next chapter, gravitation. Here I am discussing time period of Earth with about its own axis. About its own axis. Time period of Earth's rotation about its own axis is proportional to square of the radius of Earth. Square of the radius of Earth. For example, if radius of Earth decreases to r by 2, half of the present value, then what will be the time period of Earth's rotation? If r decreases to r by 2, t proportional to r square, t dash proportional to r by 2 all square, then we will get what? T dash equal to t by 4. What is the time period of rotation? Nowadays it is 24 hours. 24 by 4, it is 6 hours. That means what? If radius of Earth is reduced to, or Earth shrinks to half of the radius of half of the current radius, then time period of Earth's rotation about its own axis will reduce from 24 hours to 6 hours. That is what discussed by this proportionality, t proportional to r square. Here again I am repeating, this time period is not the time period given in Kepler's laws. It is the time period of rotation of Earth about its own axis. linear motion, rotational motion. First point, if linear acceleration is 0, if acceleration is 0, velocity equal to constant. For velocity they give the symbol u, then velocity equal to displacement by time, and displacement equal to velocity into time. Like that in angular motion or rotational motion, we can see if angular acceleration alpha equal to 0, then omega equal to constant. Then we can say omega equal to angular displacement by time theta by time, simply that is theta equal to omega into t. And in uniformly accelerated motion, if acceleration equal to constant, we can use equations of kinematics and we can make equations of rotational dynamics. Then there we will apply angular acceleration alpha equal to constant. Displacement is equal to u plus v by 2 into t. U plus v by 2 is average velocity in uniformly accelerated motion. Like that in rotational motion, theta equal to omega 1 plus omega 2 by 2 into t. Omega 1 is the initial angular acceleration and omega 2 is the final angular acceleration. Like that we can give omega instead of velocity, alpha angular acceleration instead of a, and theta instead of displacement. Then we will get all the 6 equations of kinematics in rotational motion also. Omega 2 equal to omega 1 plus alpha t, alpha equal to omega 2 minus 1 by t, theta equal to omega 1 t plus half alpha t square, and omega 2 square equal to omega 1 square plus 2 alpha theta, and theta n, nth angular displacement in nth second, omega 1 plus 2n minus 1 into alpha by 2, or half alpha into 2n minus 1. This equation we once discussed in the chapter motion in a plane. If acceleration is constant, not constant means acceleration changes with the time. That means acceleration is given in the question as a function of time. Okay, angular acceleration is given as a function of time. Then omega we can calculate d theta by dt, and alpha we can calculate d omega by dt or d square theta by dt square. For linear momentum, p equal to mass into velocity, or we use root of 2m into kinetic energy. So for angular momentum we can use I omega or root of 2 into, instead of mass, moment of inertia, kinetic energy. Like that. For kinetic energy we can half mv square is the equation in linear motion, but in rotational kinetic energy equal to half I omega square, or kinetic energy equal to p square by 2m. Like that in rotational motion, kinetic energy equal to L square by 2I. And for force we use F equal to ma, and for torque we have to use tau equal to I alpha. Again comparison, rotational motion, translational motion. For work in translational motion we use integral f dot ds. In rotational motion we use integral tau dot d theta, and for power we use f dot v, and for power in rotational motion we have to use tau dot omega. We are going to compare rolling, slipping and spinning. You just see the diagram, then I will explain. In the first diagram, translation, slipping is given. The wheel moves linearly on the surface. It is called slipping, that is only translational motion. Then you can see velocity of any point of the wheel is same, that is v. At A, B, C and D. Second wheel is in rotation or spinning. Second wheel is in rotation or spinning. What does it mean? There is no translation. There is no translation. So, every point of the wheel moves with the same speed. Don't say with the same velocity, because direction of velocity changes along the tangent. You can see, observe the third wheel. When the body just begins to roll, velocity at the bottommost point is 0 and velocity at the topmost point at B, velocity is 2v, and velocity of C, center of mass, is v. It is not marked with the velocity of center of mass is v, and velocity of the point D is root 2v. Rotational kinetic energy rotation, common equation is half I omega square. Instead of mass we will use momentofinertia, and instead of velocity we will use omega. Half I omega square. Okay, half into, for I we can write mk square, where k is the radius of gyration, and v equal to r omega, and then omega equal to what? V by r. For radius we are giving capital R, so we will get v square by r square. So kinetic energy rotation equal to half mv square into k square by r square. Half mv square into k square by r square. Okay, for a ring and thin hollow cylinder, k square by r square is 1. For disc and solid cylinder, k square by r square is 1 by 2. For solid sphere, k square by r square is 2 by 5. And for hollow sphere, k square by r square is 2 by 3. That we already discussed. By knowing k square by r square, we can compare kinetic energy rotation of different spinning bodies. And next one, rolling motion. Okay, rolling motion is the combination of translational motion and rotational motion. So kinetic energy rolling equal to kinetic energy translation plus kinetic energy rotation. Kinetic energy translation equation is half mv square, and kinetic energy rotation we just discussed what? Half mv square into k square by r square, or you can give half I omega square. So we can take a half mv square outside, then we will get 1 plus k square by r square. This is the equation of kinetic energy rolling. Or we can say half mv square plus half I omega square for kinetic energy rotation, or you can use L square by 2I. K rotation equal to half mv square into k square by r square. This is the general equation of kinetic energy rotation. For ring, k square by r square equal to 1. So we can say kinetic energy rotation equal to what? Half mv square. Kinetic energy rotation of a ring is equivalent to kinetic energy translation. Then what is kinetic energy of rolling for ring? Kinetic energy of rolling for ring is kinetic energy translation plus kinetic energy rotation. Half mv square plus half mv square, it is mv square. It is mv square. So we can say during rolling, 50% of kinetic energy is rotational and 50% kinetic energy is translational for a ring. Once more, during rolling, 50% kinetic energy is rotational and 50% kinetic energy is translational for a ring. Okay, and this condition is same for hollow cylinder. So we can say for a ring or a hollow cylinder, kinetic energy rotation and kinetic energy translation is 50% of kinetic energy rolling. For disc or solid cylinder, kinetic energy translation, normal equation half mv square, and kinetic energy rotation, our equation is half mv square into k square by r square, it is 1 by 2 for disc or solid cylinder. So we will get 1 by 4 mv square. Kinetic energy rolling means total kinetic energy translation plus kinetic energy rotation. So we will get half plus 1 by 4 is 3 by 4. 3 by 4 mv square is the kinetic energy rolling. So we can say 1 by 4 is 1/3 of 3 by 4. 1 by 4 is 1/3 of 3 by 4. So we can say 1/3 of kinetic energy rolling is rotational and 2/3 of kinetic energy is translational. 1/3 of kinetic energy is rotational and 2/3 of kinetic energy is translational. 1/3 means 1 by 3 into 100. When we are converting into percentage, it will be 33.333 something. So 33.3% kinetic energy is rotational and 66.6% kinetic energy is translational for a disc or for solid cylinder when it is rolling. Okay, like that we can say conditions of solid sphere and hollow sphere. All are given as a table on the board. You can see it. For solid sphere, k square by r square is 2 by 5. Translational kinetic energy same for all, half mv square. And for rotational kinetic energy, solid sphere, it is 1 by 5 mv square. And total is 7 by 10. So we can say 28.5% is rotational Ke and 71.5% is translational Ke. A body rolling on an inclined plane of inclination theta from a height h. Then what we can say? At the maximum height, it possesses potential energy and the body rolls down. When it reaches the bottom, it possesses kinetic energy of rolling, kinetic energy translation plus kinetic energy rotation, and it just starts rolling from the top. So its initial velocity is taken as 0. Then what will be the displacement traveled by the body? Displacement is the path, displacement is the length of inclined plane. Okay. From here we can say sin theta equal to what? Opposite by hypotenuse h by s. Then displacement s equal to what? H by sin theta. This is the displacement traveled by the body when it reaches from height h to the bottom. Displacement s equal to h by sin theta. Now, what will be its velocity when it reaches at the bottom? We can say according to law of conservation of mechanical energy, potential energy at the top equal to kinetic energy at bottom. Potential energy at the top equal to kinetic energy at bottom. Potential energy at the top we can give mgh and kinetic energy at bottom we can give half mv square into half mv square into 1 plus k square by r square, because here we have to take kinetic energy of rolling. Half mv square into 1 plus k square by r square, cancelling m, we will get velocity from here. What is velocity square? Velocity square equal to 2gh by 1 plus k square by r square. Then velocity at bottom equal to root of 2gh by 1 plus k square by r square. This is the velocity of the body at the bottom when it reaches the bottom. Then how to find acceleration of the body during the motion? We can say, we can use equation v square equal to u square plus 2as. Then v square equal to what? U is 0, 2 into acceleration into displacement. So acceleration a equal to v square by 2s. V is here, then v square equal to 2gh by 1 plus k square by r square. 2gh by 1 plus k square by r square into 2s. What is displacement? H by sin theta. H by sin theta. 2h cancelled. Sin theta will go to the top. K square by r square. Sin theta will go to the top. Then we will get acceleration equal to what? G sin theta by 1 plus k square by r square. G sin theta by 1 plus k square by r square. It is the acceleration of the rolling body on an inclined surface. How to find time of descent? Time taken by the body to reach the bottom. To get that, we are using v equal to u plus at equation. So time t equal to u is 0, right? So time t equal to velocity by acceleration. For velocity, we got the equation root of 2gh by 1 plus k square by r square. And for acceleration, we got the equation g sin theta by 1 plus k square by r square. G sin theta by 1 plus k square by r square. So time t equal to 1 by g sin theta. We just imagine 1 plus k square by r square as x. So here root of 2gh by x by g sin theta by x. So what will happen? This x will go to the top. So this will become inside the square root. So we will get root of 2gh into 1 plus k square by r square. Now we can take this g to the square root. So we will get g square inside the root. 1 g will cancel. So time of descent t equal to 1 by sin theta into root of 2h by g into 1 plus k square by r square. This is time taken by the body to reach the bottom. By knowing k square by r square value, we can compare acceleration, velocity and time of descent of various rolling bodies. So we can conclude that as k square by r square decreases, as k square by r square decreases, velocity while reaching the bottom increases. Because for velocity k square by r square 1 plus k square by r square comes out on the denominator. And the acceleration also increases, because for acceleration equation g sin theta by 1 plus k square by r square. But time of descent decreases. That we already know. If velocity increases, it will take lesser time to reach the bottom. So time of descent decreases. Here is one more table for you to understand the concept of rolling. Okay. You can see body rolling or hollow cylinder, k square by r square is 1. Velocity equation root of 2h by 1 plus k square by r square. For ring we will give k square by r square as 1. So 1 plus 1 2, that will be cancelled. So for ring velocity will be a root of gh. And its acceleration will be half g sin theta, and the time of descent will be 1 by sin theta into root of 4h by g, because k square by r square equal to 1 for the ring. Like that we can calculate, or we can say separate equations for different bodies. They are explained in the table very accurately. Solid sphere, hollow sphere, disc or solid cylinder, okay, like that. So you can see the second column, that ring and hollow cylinder k square by r square is 1, disc or solid cylinder k square is 1 by 2, k square by r square is 1 by 2 or 0.5, for solid sphere it is 2 by 5 or 0.4, for hollow sphere it is 2 by 3 or 0.66. Comparison of sliding, freely falling and rolling from a inclined surface. For rotation, radius of gyration not equal to 0, but for translation and all other types of motion except rotation, radius of gyration equal to 0. That means radius of gyration k is defined only in rotational motion. Only in rotational motion. So you can see in the table, for rolling k square by r square not equal to 0, but for sliding and falling k square by r square equal to 0. You can see the diagrams, velocity, acceleration, time, that we already discussed. And in sliding motion, velocity equal to root of 2gh. Due to gravity effect, we will take only the vertical height, that is why root of 2gh, or we can give k square by r square equal to 0. Then you will get root of 2gh, and acceleration is g sin theta, and time 1 by sin theta into root of 2h by g. And in case of falling, in case of freely falling, velocity while reaching the bottom is also root of 2gh, and that acceleration is g, that we already know. Okay, and time of freely falling is also, we already studied in the chapter motion in a straight line, root of 2h by g. And here this chapter rotational motion is over here. I tried to include all the concepts of the chapter. After watching this video lecture, you just download the study material and questions with solutions given in the description box and try to solve them, and then you will understand the entire concept of the chapter very clearly and thoroughly. Okay, next chapter we are going to discuss is gravitation. Best of luck, keep going good.